Hi, welcome to Expertisor Academy. This is Giri, lecturer Felix. In this video, we discuss about the relation between small f, that is focal length, and radius of curvature, capital R. So, before entering this relation between focal length and radius of curvature, we should know about the what is focal length, what is radius of curvature. First of all, we consider the any curve mirrors. For example, concave mirror or convex mirror. Here, for concave mirror, the reflecting surface is inside, the non-reflecting surface is outside. The geometrical center of the mirror, that is pole. If the light rays are coming from some infinity distance after reflection, these reflected light rays are meeting at one point. That point is called focus point. The center of this total curve mirror, that is center of curvature. Okay, so this is the concave mirror. For convex mirror, inside of the mirror is non-reflecting surface, outside of the mirror is reflecting surface, so that is convex mirror. So this is the pole, this is the focus, this is the center of curvature. So the focal length small f is nothing but the distance between pole and focus is called focal length. Next, the distance between pole and center of curvature is called radius of curvature. The distance between pole and center of curvature is called radius of curvature. Okay, so let's verify the relation between focal length and radius of curvature. So let's see the center of curvature of the mirror. So C is the center of curvature of the mirror. Consider a light ray parallel to the principal axis is incident on the mirror at M. So consider this is the light ray which is parallel to the principal axis, is focused on the mirror at point M and passes through the principal focus after reflection. So this is the incident light ray, this is the reflected light ray, so which is passing through principal focus. Consider one normal line from C to M. So this is the normal line. So here I is the angle of incidence in between the normal line and the incident light. At the same time here, this is the reflection angle of reflection, so which is equal to angle of incidence. So that's why this is I. So which is equal to this angle, that is also I. So this is incident light, this is reflected light. P to M. So this distance represents the height of the incident light focused on the mirror from pole or principal axis, or simply height of the point of incidence from the principal axis. Okay. For convex mirror, this is the incident light, this is the reflected light. Here, this is the normal line, this is angle of incidence, this is angle of reflection. Here, this is angle of incidence. So this is the point of incidence. So from the mathematics, particularly in triangles, the sum of the angles exterior that is equal to sum of the angles interior. So I plus I that is equal to 2I. The geometry of reflection of incident ray is focused in the shown in the figure. The line CM is normal to the plane or normal to the mirror at M. CM is the normal line. Let I be the angle of incidence and the same will be the angle of reflection. So I is the angle of incidence, I is the angle of reflection. So why? Because from the second law of reflection, I is equal to R. Let's go for the derivation part. If MP is the perpendicular from M on the principal axis, then from the geometry, the angles MCP that is equal to I, MFP that is equal to 2I. MCP that is equal to I, MFP that is equal to 2I. From right angle triangles, triangle MCP and triangle MFP, triangle MCP and triangle MFP. So tan I is equal to, from MCP, tan I is equal to PM divided by PC. PM divided by PC. Tan 2I that is equal to PM divided by FP or PF. As the angles are small, tan I is identically equal to I, tan 2I is identically equal to 2I. So I is equal to PM by PC, 2I is equal to PM by PF. So consider here PM. This is the height of the point of incidence. PC is the radius of curvature. PF is the focal length. So at the place of I, we take the PM by PC. So here PM cancel. So after cross multiplication, 2PF that is equal to PC. So by using the diagram, PF it's nothing but focal length. The distance between pole to focus is called the focal length. So that is 2F. PC, the distance between pole to center of curvature, that is capital R. So capital R is equal to 2F. So simply the radius of curvature is the distance from pole to center of curvature. So this is the double distance for the focal length. So focal length is nothing but the distance between pole to focus. So in this derivation, here we took the two different triangles FMP, CMP. So by using these two triangles, here we calculated the relation radius of curvature capital R is equal to 2F. So this is the relation between focal length and radius of curvature. So thanks for watching this video. For more videos, visit www.expertisoracademy.com. Thank you.